reading KSP or solubility constant. This is the pre-lab for experiment 6. Another application to Le Chatelier's principle. So what we are trying to do in this experiment is to measure solubility product constant or KSP for calcium hydroxide using titration. And also we want to study the effect of common ion in the solubility of calcium hydroxide using the Le Chatelier's principle. So we will do the titration. The titration that we are doing, we are using standard HCl. And when we use standard HCl, we can calculate concentration and do the titration. We can calculate concentration of hydroxide ion. This reaction is at equilibrium, okay? Because it's at equilibrium and the only source of hydroxide ion is coming from the calcium hydroxide, and calcium ion also is coming from calcium hydroxide. For every 1 calcium hydroxide, we get 1 calcium ion and 2 hydroxide ion. So if you find concentration of hydroxide ion, we can divide that by 2 to get concentration of calcium ion. So in other words, concentration of calcium ion is half the concentration of hydroxide ion. Solubility product, KSP, is written based on concentration of the reactant only. So we have calcium 2+ and hydroxide ion concentration, okay? So we need concentration of hydroxide ion. We are going to do the titration first and find the concentration. Basically, you find the molarity, and then you divide the molarity of hydroxide by 2 to get the concentration of calcium hydroxide. On the second part of this experiment, the calcium hydroxide solution that we are using is not dissolved in pure water, is dissolved in another calcium chloride solution or calcium ion solution. So basically, the solution of calcium hydroxide is in, let's say, 0.1 molar solution of calcium chloride, but that number is not given to you directly based on this experiment. And we don't need that. Okay, here's how what's going to happen. In this case, the formula still is the same. So for the solubility, you can just, when you get the concentration of hydroxide ion, you divide that by half and say that is the solubility. So molar solubility is 1/2 of the hydroxide. We are not going to say molar solubility equals to the concentration of the calcium, because calcium has 2 sources here. One is calcium hydroxide and one is a calcium chloride. So we only use concentration of hydroxide ion in order to determine the solubility or molar solubility. When you perform this experiment, you will notice that. I mean, of course, you could do calculation and find out based on, and setting up ice table and say how much calcium ion is already there and how it's going to affect the value for concentration at equilibrium of the calcium ion, which is the solubility. The other approach, like experimental approach, would be to set up a burette with the HCl. So if you have HCl here, 0.05 molar HCl, and then you get a pipette, and using a pipette, you add the calcium hydroxide solution, and you add proper indicator and add enough of the HCl to neutralize all hydroxide ion. and compare in experiment 1, which the calcium chloride, the calcium hydroxide is just a saturated calcium hydroxide solution in water, to experiment 2, or the trial 2, or part 2 of this experiment, when you have calcium hydroxide dissolved in calcium chloride. So for the second one, if you use slightly less HCl, okay, use less HCl, that is going to tell us the solubility has changed. So in general, solubility is going to decrease because of the presence of the common ion of calcium. Okay. You're going to follow the procedure if it asks you to show all your calculation of the concentration of the calcium ion, or you just use the concentration of the hydroxide ion based on the values that you find from the HCl used, the amount of the HCl used. At the equivalence point, number of moles of HCl equals to number of moles of hydroxide ion, and that gives you the concentration for the hydroxide ion. And you divide the concentration by half, that would give you the concentration of calcium ion.